On slide 60, I turn to step 3, model 2. And just to remind you, step 1 is the 2-level basic step. Step 2 is the regular 2-level modeling. And step 3 is the 2-level modeling, taking time into account in the model explicitly. And now we come to model 2 in step 3, where we want to add a random residual variance. And the reason we're doing that is because of our observation in step 1 in the between level scatter plot of the positive affect variance and mean. We saw first of all a strong variation in the variance, heteroscedasticity, and a correlation between the variance and the mean. So if you look at the within part of the model, we have now put a filled circle for the residual variance going into the positive affect on within. And that means that that variance will change over individuals on the within level. So the within level residual variance will change, will be different across individuals. And that's what we model then as a continuous latent variable on between, and we let them correlate. So we would expect this correlation to be negative. And this residual variance can be interpreted as variation in what's sometimes called innovation or random shocks. That is, different people reacting in different amounts to certain events. And that then is the residual influence here that is different. Now, the random autoregressive lag 1 can also be added. There would be a filled circle on that arrow. We're not going to do that in this step. That's interpreted as inertia, so individual differences in inertia. How do we do the analysis in Mplus? Well, all of this is the same in the variable command. We use Tinterval settings that are the same, but now we add in the analysis type the word random, which then makes it possible to define a random residual variance for the positive affect variable, and we call that log v. And we discussed very briefly early on what that means, why we're talking about the log of that variance, and I will talk about it in more detail, more statistically oriented detail in a few slides. And that then becomes a random variable on between, where we let the two, the mean and that variance, correlate or covary. In this run, we're also going to use the SAVEDATA command and save a file that we're going to take a look at in detail. So that's the file that will contain the variables used in the analysis, including what the time variable is that's used for the analysis by Mplus statistical machinery. On slide 62 then, you see the number of time points here for different individuals, 240 individuals. They are the clusters. And we see here, for instance, that cluster ID 45 has 6 rows in the data, and it goes up to 83 rows, that is 83 time points for some clusters. And the mean lies somewhere somewhere in between. Now on slide 63, let's think about this and note that the number of time points per individual in a run using the Tinterval option will include time points with missing data that was inserted by Tinterval to synchronize the timing, and that's what we discussed in early segments of this talk. And then look, for instance, at the first individual on the list that we just looked at, ID equals 45, which has 6 time points. Going back here, 6 time points. But 4 of those time points have missing data, it turns out. To see the number of time points without the inserted missing data, you do a run without t-interval, and that's what we did in the step 1 type equals 2 level basic run. And there the data summary, if you go back to that, shows that this ID, number 45, is observed at only 2 time points. So 4 of the 6 have missing data that are inserted to synchronize. So ID 45 does not contain very much information for our analysis. And it is important to have sufficient number of time points without missing data when estimating random effects such as regression coefficients, because the estimation is based on computing the random effect value for each individual, for which n is the number of observed time points. So that's in line with our n equals 1 analysis that we talked about. And here's a good paper that's on the DSEM special topics list of references. You know, special topics in the left margin of the Mplus homepage. Practical Aspects of Dynamic Structural Equation Models is a technical report that we keep adding on to when we get user questions that have not been covered in the report. Slide 64 then shows the results, and I actually included the model results first without log v here at the top, so that's just repeating what I showed you for model 1, step 3 model 1. And at the bottom we have with log v. So if you look at the bottom part of the table, which has to do with the log v run, then we see that the autocorrelation is changed a little bit, but not that much. And the residual variance, 0.483, is now a random variable, so it won't be listed on the within level. Instead, that variance shows up in terms of log v on the between level, the mean of that log v and the variance of the log v. And what we're going to try to do in detail here is translate that back into the variance, so going from log v to v. But for now, we're just going to observe that the variance of the log v has a positive confidence interval, does not cover 0, as variances don't in Bayes. And we may take a look at the ratio of the two, as we talked about before, and that's clearly much greater than 3. Again, ST, the posterior ST, being analogous to the maximum likelihood SE, standard error, so that the ratio is analogous to a z-score, the z-test. So this is a substantial amount of variation in the log v. You may also want to take a look at this MBR article, an earlier article from 2015, where they talk about biases in the results when ignoring the random nature of the variance, of the residual variance. In that analysis, I believe there was also a random autocorrelation, which was a driver, really, that correlation was the driver of the bias. Now, to understand what's going on here with the log v and being interpret that to get a feeling for how big that variation is in the variance, let's take a statistical look at this. So the variance, we're talking about the variance of epsilon, the within level residual variance. And we, in Mplus, we specify that that variance has a log normal distribution. You know, it's a variance, so we want it to be greater than 0. And we know that variances have a skew distribution, a long right tail. And here is a plot of those kinds of log normal distributions for different parameter values. So it gets a particularly strong skew when the variance is large for the log normal. So this is and gets more normal looking when the variance is smaller. Now, because v has a log normal distribution, the log of v has a normal distribution. So that's why we work with log V instead of V, because Mplus wants all of its random effects to be in the normal distribution family. So that fits with the assumption of normally distributed random effects in Mplus. Now the log normal distribution for log V, or for V, the log normal distribution for V implies that V has median e to the power of the mean of the log V, which is printed out in the output. And the mean is the e to the power of the mean plus the variance divided by 2. And there's also an expression for the variance. And in some writing, you may see an equivalent way of expressing this, where you say that the variance of epsilon is e to the power of s, where s is the variance, e to the power of s, so that the variance is by necessity greater than 0, which we want, and therefore taking the log of that, log of e to the power of s is s itself, has a normal distribution. So that's another way of expressing it, except I think it's a little clearer to say that we make an assumption about the distribution of V, that it has a log normal distribution, and therefore the log V gets a normal distribution. All right, let's go a little bit further here. Repeating the picture, and I'm stating then that for a skew distribution, like the log normal, quartiles are better summaries than means and variances. It's not like you can have plus minus 1 standard deviation telling you something away from the mean, telling you something important about the non-normal skew distribution. And interesting is that the quartiles can be obtained from the normal log V distribution, so which is the distribution we work with here in the program. And we can, for instance, consider quartiles 25 and 75, because half of the distribution lies between those quartiles, obviously, and that is 0.675 standard deviation from the mean. Because the log normal is a monotonic function of the normal, the quartiles, therefore, are obtained by exponentiating the normal distribution quartiles. And don't worry, I'm coming down to Earth after this excursion into the stratosphere of statistics, and on slide 67. So the quartile estimates and their confidence intervals are obtained by adding a model constraint run again with parameters from model. So we label on between the log V mean and the log V variance, and then we express these quartiles, the median being the 50% quartile and the 25th and 75th quartile, and they are based on the normal distribution, mean minus square root of s. So in parentheses here is the normal 1 standard deviation below the mean, 1 standard deviation above the mean, and when we exponentiate that, we get the quartiles for V, for the variance that we want. And it turns out then that median V is 0.31, and with this CI, and that's a 50%, the lower 25th quartile for V is 0.15 with that CI, and 75th is 0.635. And we compare that to the non-random fixed residual variance in Model 1, which is 0.483. So that lies somewhere between the 25th and 75th. And we know that means tend to be overestimate being high because of a long right tail. So therefore we want to consider a median instead. So median lies in between of these two, obviously. So how does that help us interpret this? Well, if you take the square, so these are quartiles on the distribution of V, the variance that we are interested in. So it's a variance, values of the variance at those quartiles. So if you take the square root of this and this, we get a feeling for how big the standard deviation is of the variance at these quartiles. And it turns out, you may want to scribble that the standard deviation here, then the corresponding standard deviation is 0.4 for the 25th quartile and 0.8 for the 75th quartile. So 0.8 standard deviation, which then can be related to the scale of the PA variable, which is 1 through 7. So it's 0.8, 80% of a scale step on the PA scale. That's the a typical or a 75th percentile value for the standard deviation. So that tells you a little bit about how to bring it back to reality after having been presented with log V means and variances, going via the quartiles and then taking the square root out of the quartiles. All right, enough about log V then. Let's go to slide 68 and take a look at TECH4, because that has some new features also when we now work with type equals random. And just to remind you, we have type equals random because we are allowing for individually varying residual variances, so random variation across individuals. And we say then first of all that the within level covariance matrix changes over individuals when we have type equals random. So think about that in terms of the picture. The residual variance changes over individuals, and therefore the variance of PA on within changes across individuals. So the variance of PA changes across individuals. And what TECH4 does is to give you average over individuals for within. So you compute the variance for each person and take the average over that. So that would be down here for the covariance matrix, 0.642 is the average. It's going to be fairly close to the between level part of TECH4. All of this is within level part, but not exactly the same. It's like doing repeated n equals 1 analysis and then taking the average. It's not exactly the same way of estimating it, but they are aiming for the same quantity. Now, what may be surprising, and here then for log V, we don't have any between level variation here. Sorry, we don't have any within level variation for log V. It's a between level variable. Now, still here, this may be confusing, the means for these latent variables appear on within. Usually they appear on between, but you know, each person gets their own log V value because it varies across individuals. And this is the average of those log V values. Again, that's going to be close to the between level mean, the mean that you see on the between level in TECH4 and also in the regular output. Same thing for PA. And here's PA ampersand 1 is listed as well. That's sort of unnecessary because they're going to be the same. And here too, because of stationarity. So that's a little tricky at first, and but I just want to make you aware of it. I don't know how important it is, but there it is. Slide 69 though. Slide 69 is a useful piece of information. If you remember in the input, at the bottom of the input on slide 61, we added a SAVEDATA command, and where we save the file PA for tinterval2.dat, and that file is then the data that were analyzed. So the variables that were analyzed, and including the time variable that Mplus created. And the order format of the variables is as always listed, the positive affect first and the lag positive affect, and then the hours variable, which is in the original data, and then the underscore new time, which is the midpoint. I'll write it down here. Midpoint of time ranges implied by t-interval. It's only used in the time interval plot, which we're going to take a look at in a few slides. And then time, which is the variable that name that you give for the time that Mplus creates. Going from 1, 2, 3, the bin number essentially, or exactly actually, given by the user, created by time interval using analysis, same as the bin number. If you don't give any name, the default name is underscore bin t. So those variables, you may want to take a look at those and compare the original hours with the time that Mplus created and see if there's a big discrepancy. On slide 70 then, we take a look at some of the first rows of SAVEDATA for this person, ID equals 20 under time interval 2. And as you look at this, you want to compare with slide 14 showing in detail what t-interval does to the data. So what we have here is the original hours variable. The person sleeps, wakes up at 5, and is observed again at 7, 10, 11, etc. And the analysis time that you use in the computation is this bin time, just integers 1, 2, 3, etc. And new time, underscore new time, is giving you the midpoint of the bin interval that we're talking about here. And for instance, the problem here was for these time points for this person was that observed time point 10 and 11 ended up in the same bin, in the the 10 to 11 bin, which is corresponding to time 6. So we had to move 10, the earlier hour, into an earlier bin, the 8 to 9 bin, and therefore we get a misalignment between the actual time that positive affect was recorded and the time that is assumed by the new time variable. So you get a discrepancy here, 10 and 9, whereas 11 stays in the right time bin, the 10 to 11 time bin, which is time 6. So you see then that misalignment at 10 a.m., 10 and 11 in the same 2-hour bin, 10 is moved to earlier. And as we're going to see in a few slides, this kind of misalignment can be looked at in plots. There's a so-called time interval plot for each individual on slide 72, where you see the observed time versus the new time, and you see the discrepancy, and the discrepancy is measured for each individual and each individual's time point. And we actually have a message warning the user of 2 big discrepancies. Now, one thing we can note here is that there's a lot of missing data then, of course, early in the morning and perhaps late at night as well. But that could be good to capture the fact that auto regression between the last measurement in the evening and the first in the morning should be quite low, and therefore it's in a rough way takes care of the nighttime issue. But the nighttime issue is a research topic, and here we're only handling it in a rough way. You may also ask yourself if the nighttime autoregression is the same or different than a daytime autoregression for the same time distance. You can explore these things in the real data and perhaps try to incorporate it into the model. I don't know how much of a difference it makes in practice, but it could be worth studying.